welcome back. Today we will start with another issue other than the non-linearity what we have discussed. In satellite communication another issue comes up, that is called synchronization. You are familiar with this word synchronization. So, let us see what are the issues and techniques used in case of satellite communication about synchronization. Okay. So, in the synchronization mainly what we will be covering is frame synchronization and network synchronization. So, let us first see what is the need. Now, to recover the symbols what is transmitted by the transmitter at the receiver side, we need to locally generate replica of the carrier frequency and phase using phase lock loops, and also that is to demodulate, and also we need the symbol start and symbol end time, which is symbol clock. These are required at the demodulator. Now, this is called carrier phase and symbol synchronization. You have studied this in your BTech courses. So, what is further required is at higher level when these informations are sent in frames, and most of the time it is sent in frames, like in internet communication, internet protocol use packets, that is a form of a frame, or in TV transmission they use the TV frames in digital video via satellite, digital video broadcast via satellite, also in other cases. In most of the cases it goes in the form of frames. Now, this frame beginning and the end of the frame, where the frame starts, where the frame ends, that receiver has to know, and to locate that, the type of technique which is used is called frame synchronization. And there is one more thing, that is satellite is a resource which is covering a wide area, and that area when it is covered, so many users are trying to access the satellite resource. So many transmitters are there. We have seen this example in ATM and other cases. So, these transmitters have to send their signals and has to reach the receiver at the satellite, and in particularly in case of time division multiple access TDMA, they have to reach in proper sequence as per the allotted burst sequence. So, since many transmitters are trying to access this, we can call it network synchronization. So, we will discuss this frame synchronization and network synchronization in subsequent periods. So, let us see the frame synchronization. This by definition it is to help the receiver detect the start and end of a frame. The transmitter uses some special signaling technique, which is nothing but some identification that this is the start of the frame or this is the end of the frame, when the frame size varies, and in some cases only the start of the frame and the frame size is known by the receiver. In some cases frame size is also not known, but only start of the frame, and then it gives the length of the frame. So, anyway you have to know the start of the frame, where the actual bit starts, and that contains many fields, what type of frame it is. It may be containing data, it may be containing the control information. There are many types of frames out there. So, therefore, the start of the frame identification is very important. So, receiver has to detect the start and end of the frame. Now, this could be done by the transmitter by sending a single bit identification of a frame, or it could be multiple bit, a sequence of bits. It can be called as a frame markers. So, let us see. Receiver should know the frame marker pattern and what is the repetition rate of that repetition interval of that frame marker, then only it can detect where the frame marker is. So, let us see that receiver then correlate the incoming data stream with the known frame marker and find out where the frame marker matches, and then he knows that this is the received bit stream where this frame marker has matched. So, this is the frame synchronization that starts. Pictorially it is like this. Let us say small n bits is a 1010 pattern. It repeats after capital N bits, 1010 pattern. That capital N bits are the data pattern, which could be random. It can start with 0 or 1 or anything, but the small n bits are repeating at certain interval after capital N bits. This is the data stream which is coming. whereas the receiver knows this pattern 1010, and this n bits he tries to match where this pattern appears, and previous to this pattern and later the trailing part of the precedence and trailing part of the pattern, he sets it as 0. So, with this pattern he tries to lock. So, receiver generates a local frame marker replica, and with that it tries to lock. So, marker could be single bit, it could be multiple bit, as we said. So, let us see the advantage of single bit marker. If I have a single bit marker, then I have to go on seeing after many such markers and finding out whether the markers have come correctly or not. So, therefore, single bit marker needs accumulation of sufficient number of correlation to decide whether synchronization has occurred. That means it takes time. So, acquisition time is long, and also the data has to come in continuously. So, there has to be continuous data stream. It should not be one burst and then stops. There are burst communication, there are continuous stream communication. So, the data has to be, acquisition time has to be long, will be long, and data has to be continuous. There is one more problem, because there is a single bit marker, the system which uses byte oriented processing, they face a problem. A simple example is T1 carrier is a structure which where frame consists of 24 voice channels of a byte each. So, 24 into 8 is 192 bit is a frame. Now, if it is a single bit marker, which is normally used, single bit marker makes it 1 plus 192, that is 193 bits, which is not divisible by 8. So, the 8 bit processor system which is trying to detect and subsequently process it becomes difficult for it, a little more complex. So, that is another complexity that comes in single bit marker. It takes time, as well as this type of problem appears. So, multiple bit synchronization code words are used, and generally this is used at the beginning of the frame as a header, and obviously acquisition time is less, because if it is detected immediately, you know, you do not have to accumulate many such things. And selection of the code word length and its pattern is it depends on the probability of false detection. By chance, in the data stream itself, if this similar pattern comes, then it will be detected as the beginning of the frame. In between the frame, in the data pattern, if it comes, that will be a problem. So, therefore, the selection of the pattern as well as its length is important from the false detection point of view. And in real life, there are errors. So, even if it is correct data frame, if there is a error appears in that, then you will miss that. So, it is a missed detection that will increase. So, correlation process becomes complex. Here also correlation process is complex. A good pattern can be, or we can use the word code word or unique word. Normally this word unique word is it's a unique pattern. So, unique word, it is this term is used. So, unique word should have low correlation side lobes. You know what is the correlation side lobe. Here it is shown as Ck is a summation of j equal to 1 to n minus k, xj and xj minus k. The pattern is xj and shifted pattern is xj minus k, k bits shifted. K is the number of bit shift and n is the length of the unique word, and xj can be plus minus 1. So, with this the side lobes has to be low if the code word selection, the xj pattern is a good quality. There are many such codes detected. Earlier it was Barker code, and subsequently many codes are detected. But there are two properties characterize this unique word of the channel with error. We have seen these two properties earlier, we have mentioned this earlier, which is called misdetection, probability of misdetection, PM. When the error occurs in the code word itself, then detection will be missed. So, it is misdetection. And false detection, when error in the data bit, in the data pattern itself, either with the error it may look like the sync word or it may look like the unique word. So, this probability of misdetection, false detection, and that you have seen, we will see it little more further on that. Exact time of the burst occurrence is not known in advance at the receiving station, let us say at the ground at the receiving station, or it could be at the satellite, because the satellite will be drifting. So, the exact time is not known, and sometimes the bursts are getting corrected for their position, TDMA bursts. So, because of that also the exact time is not known. So, there has to be synchronization. So, Unicode detected pulse should start the processing of the information. So, Unicode detection is very important for that, from that point of view also. It shows, this particular slide shows detection of Unicode identifies start of the burst, and burst could be reference burst or user burst. We have seen in TDMA discussion about this, beginning of that. So, it shows that is in the data pattern there are random bits, then CR/BTR is carrier recovery and bit timing recovery bits, which is required at the demodulator, for the demodulator. So, there are some bits which has a training pattern, it may be ones or 1010 or some pattern, which is a known pattern, and then these Unicode bits, let us say n number of Unicode bits, and after that data starts again random bits. So, Unicode bits will be repeating after frame time, and Unicode bits before Unicode bit comes, there is a known pattern is coming, and after that it is deterministic, it is preceded by deterministic bits, and it is later trailed by random bits. This you remember. Okay. This is also used as a, this Unicode pattern is used as a time mark for the reference burst, and this reference time mark per frame is used as a frame synchronization, and the burst clock synchronization. Within the frame there are bursts, so that burst clock also can be synchronized with this. This type of thing, what I am telling is shown in the blocks, that is received data and clock is going through the shift register, and there is a known and stored Unicode pattern which is known by the receiver. They are compared bit by bit, and Unicode detect pulse comes. This is obvious. The Unicode detection depends on the channel BER, and due to the error that could be there could be a detection miss, or there could be a false detection, that we are repeating. So, probability of false detection can be reduced by looking over a small time window when the Unicode is expected. Instead of looking everywhere over the complete data stream, if we know where the Unicode is, there I create a window, and within that if you look, then false detection obviously will be false detection will be much less. So, frame duration has to be known a priori for that obviously, and the frame duration and its repetition is it is fixed for a network with a known traffic. Pictorially is shown that received frames containing reference burst and user burst, and there are some apertures open, and these apertures are the frame time or frame bits, number of bits in the frame f part, and aperture will be the slightly larger than Unicode bits, that Unicode plus minus I number of bits. That I number of bits is important to know what should be the my aperture, how long I should search, and if it is very large, then there is a possibility of more false detection. So, compare bits within the time window only, and window repeats at the frame rate. Probability of misdetection can be reduced by, that is probability of false detection reduction by aperture technique, and probability of misdetection can be reduced that okay, if there is error I tolerate that error. So, I allow some amount of error in the Unicode up to a threshold, let us say epsilon. Now, let us see the sync word detection, how it is done. Receiver correlates the receive word with locally generated word, it should have a good autocorrelation function. Now, this similar type of block diagram, but with a error threshold now. So, that is received pattern in shift register, locally stored expected pattern in a register, and in the modulo 2 comparison of the patterns, and then we get some errors. So, that residual error is compared with a threshold comparator. We set a threshold, error threshold epsilon, and error level is compared. If it exceeds the error threshold, then we say its Unicode is detected, the pulse is detected. So, it can be said mathematically, that is the SI is the received signal vector in the shift register, UI is the stored signal vector in the detector, and EB is the number of disagreement when you do a modulo 2 addition over the n number of bits. Now, this probability of detection is you know this type of expression, probability of detection over with the error, tolerable error is I equal to 0 to epsilon NCI. Small p is the bit error rate probability, and small n is the length of the Unicode. So, I minus p to the power n minus I. and error threshold is epsilon. So, misdetection probability is 1 minus the detection probability, then it makes up to epsilon was detection probability. So, epsilon minus epsilon plus 1 to n, that is the misdetection probability, and NCI p to the power I 1 minus p to the power n minus I, and probability of false detection is 1 by 2 to the power n sum of 0 to I equal to 0 to epsilon NCI. Now, if the n is the burst size capital N and small n is the Unicode size, burst size means Unicode plus the data. As the burst size becomes larger than Unicode size, the probability of false detection per frame can be expressed. Probability of false detection per frame is 1 minus pf to the power capital N. This is the expression for per frame false detection probability, which will be very low. Now, Unicode is preceded by CRBT or sync pattern, which I told you it is deterministic, and Unicode is trailed by random pattern, which is a user data pattern. So, the false detection in the negatively displaced region, that is the partial sync word and the Unicode area. If that area, if you get a false detection, that has more adverse effect on the synchronization, because you detect it wrongly and you will get, I will show you pictorially how it is. Using aperture techniques such as Unicode, searching for the Unicode within the aperture, and by maintaining a smaller aperture window plus minus delta bits, the false detection probability can be drastically reduced. Okay. The aperture technique is what? So, first you say search for the Unicode with a fully open aperture. I mean, you search for all bits which are coming in till the Unicode is detected. Now, that Unicode, it may be the correct Unicode, or it may be a Unicode in the data pattern which looks like, with the error which looks like a Unicode. Then assume that it is detected, something is detected. So, Unicode is detected, then you open an aperture only after f minus delta. F is the frame rate. So, assume that this is the correct Unicode. So, Unicode will repeat after f. So, f minus delta is the aperture, there you open and look for the Unicode there. Now, if you get a Unicode there, then you are through. If you do not get it, then the first detection is wrong. If it fails to detect any Unicode when you open the aperture within this aperture, then the earlier detection was false detection, and you have to again open the aperture fully and repeat the procedure. And if you got it else, you continue for the Unicode detection in the subsequent aperture. So, like that it goes, it is aperture technique. Pictorially it can be shown like this. You see frame is f, and the small n is the Unicode pattern, and then aperture gate is n plus minus I bits, should be, and delta is the half aperture gate. That means this is the Unicode. Aperture will be opened a little bigger than that, this is the Unicode detected pulse. At the end of the Unicode you get this pulse. So, whatever the Unicode slightly bigger than that, you open the aperture, where the delta is the half of the aperture gate. Okay. And then let us say the aperture technique, that say before the actual Unicode comes, you got a false detection, and you got a false detection, you open the aperture, but actually Unicode is supposed to be detected here, where it is Unicode supposed to come here, which will repeat after here, but you open the aperture area based on this false detection. So, you will not find a Unicode here. So, therefore, you will open the aperture again fully. So, you detect it here. So, once you detect, again you open the aperture here, and now this time you will get the Unicode within that. So, if the false detection has occurred once here, and you discovered that it is a false detection after opening a first aperture, then you should go for complete open search. Now, if you get another false detection here, let us say the second false detection occurs when you have opened the aperture again. So, you will open a wrong place, another window, again you do not get the Unicode. So, you open the aperture again, you look for the correct Unicode, you get the Unicode, and then you open the aperture f minus delta, you get that. So, this is how the aperture technique works, pictorially shown. Now, the for the network synchronization, that was the frame synchronization. Now, at the network level, in a multi-carrier operation, it is preferred to pre-correct. It is preferred to pre-correct by each transmitter the parameters, so that the receive functions are less complex. I told you the example of TDMA type of thing, that at the satellite there is a receiver, and there are n number of transmitters which are trying to access in TDMA to the satellite receiver. Now, in that case, the satellite receiver, for each of the burst, it has to have the arrangement of synchronization. Instead, if it is known that the satellite at the time frame where the burst is, so the transmitters can pre-correct and transmit, so that the receiver does not have to make a complex arrangement. The complexity is distributed over the transmitter. So, that is what the network synchronization. If the pre-correction is based on, the pre-correction can be done in various ways. It can be based on predicted, that is modeled or calculated way of knowing when it is supposed to reach there, at what frequency is supposed to reach there, or it could be assisted by some external information. Somebody else has done certain measurements and supplied that information, and then it is given as a pre-correction parameter. So, it is known a priori. It should be known a priori to the transmitters, all the transmitters, for their each individual pre-correction. Then it is called open loop. You are going in one direction, so it is called open loop synchronization. There is no loop formation in this. And if the pre-correction is based on some measurement by each of the transmitter, is based on measured parameters during communication. If you want to do a measured parameter, particularly one of the important measured parameter is how long it takes to reach the satellite, that distance. So, during that time, whether my frequency is changing or time is changing or the distance is changing, the delay is changing. So, you do the measurement. That means, if the each transmitter has to do the measurement, and it is not, the information is not supplied by anybody else. So, it has to do a round trip measurement. That means, it needs a returning. It is transmitting as well as it will be receiving. So, it is called closed loop synchronization. That loop is closed. So, pre-correction could be open loop or it could be closed loop synchronization. We will see both of them. Now, it is done by pre-correcting time and frequency in open loop synchronization. Both time and frequency has to be seen. Let us go a little more deep into the subject. It is faster, obviously, because there is no return link, and it is known that a priori that when it is to be pre-corrected and sent, it is obviously less complex comparatively, and the a priori knowledge of the channel either by external source or by a model. Let us say in case of TDMA, the reference station, if you remember the TDMA lectures, there is a reference station which maintains the network, the frame timing, etc. So, it has the complete information of the satellite position, its ephemeris, as well as the position or the location of each of the stations which are participating on that. Since the coordinates are known, and in terms of time also the satellite coordinates are known, the propagation delays for each of the transmitters can be known by the reference station. So, the reference station during its reference burst transmission, it can supply this information to each of the transmitters. If you remember, in TDMA there is a reference burst, and reference burst has certain preamble and some data portion. In that data portion it can supply that time to time it will update the information of the propagation delay for each of the station. So, it is the external source knows about it, or it can be done by some modeling, that is you know the drift of the satellite, you know the sun moon drag of towards the satellite, and therefore the satellite movement can be modeled, and if that model is supplied to individual transmitters, the earth stations, they have their own location, and from the model at a particular time they can find out the position of the satellite as per the model, and as part that model it can find out what should be the propagation delay between the earth station to the satellite. So therefore it can be modeled, or it can be known by the external source. So they can supply this, and but only thing, the problem is this whole thing cannot adapt to the unplanned changes of the channel during the communication. During the communication, if there are certain changes, these are at a certain instant of time this model will work, at instant of time this information is supplied, but unplanned changes, sudden changes, it cannot track, and synchronization depends on the synchronization time depends on the tolerance of the error. So we will stop right now, and we will continue the discussion in the next period. Thank you very much.